All right, and we're live. Um, Welcome everybody to the 34th Data Science Leuven meetup already. Um, I have a few amazing speakers with me tonight. Normally we have 3 speakers tonight. We have 5. So that means you get 5 for the price of 3. I'm not increasing the entrance fee tonight, so that's good for you. Uh, um, I didn't make a slide to present or to show each of them individually, but I'll quickly introduce each of them, and then you'll get to meet them when they do their talk. So first up is Jan van den Bussen from the best university in Belgium called U Hasselt, and he's going to talk about the distributed data intelligence project. Next is Jan and Geert from Python Predictions. And Python Predictions is an organization around data science, and they've recently written a data science library called Cobra, and they made it open source on GitHub. So they're going to introduce what Cobra is, how can you use it in your data science projects. And finally, we have Sebastien and Dirk. They are from BioStrand. It's a startup from Limburg, and they focus on well, it says here biogenetics processing, but they can explain that in much more detail what it is exactly and how they use data science in their day-to-day life. We have a session planned tonight, like always, of about an hour and a half. So without further ado, let's start with the first speaker. Jan, I would say the floor is yours. For the others, I will move you to the lobby again so Jan can start sharing his screen. And I hope you all enjoy this evening. Thanks for joining. Yeah, Jan, I'm adding your slides. There they are.
Okay. Can you hear me?
Yes, thank you.
Okay. Okay, thanks for giving me this opportunity to talk to you. I actually hope that some of my ex-students are in the audience. We will see. Let me know. So I wanted to talk about a project that is part of the Flanders AI Research Program, which is a regionally funded research program that started mid-2019 and which is intended to boost AI research on a Flemish level. And it involves both all the Flemish universities and also some strategic research centers of the Flemish government. This AI research program consists of 4 great challenges. You can read more about it on that website that I show there. The 4 challenges are basically data science and decision making, then a hardware challenge, then a challenge on multi-agent AI, and finally a challenge that focuses on the human AI aspects. And I'm part in a project, in a work package, if you want, that is part of the 3rd challenge, the multi-agent challenge. And our work package is called Distributed Data Intelligence, or just nicknamed D2AI. Now, who are the people involved in this research project? People from the University of Ghent, namely Ruben Verborg and Anastasia Dimou, and many collaborators. Then at VUB in Brussels, there is Bart Bogaerts, a young professor there who specializes in knowledge representation, and his colleagues. At U Hasselt, I'm involved with my students, and at Vito, which is one of the Flemish research institutes, Bart Bulens and company. Now, let me begin by giving the 2 main inspirations that our project is born from. And these are basically 2 unfulfilled dreams. The one is to see the web as a database, and not only to see it, but to actually be able to use it as a database. And the second one is the unfulfilled dream of personal information management. So let me go into these 2 a little bit more detail. First, the web as a database, which is also called in various names, for example, the semantic web, open link data, many different names for basically the same thing. The web, as we all know it, it's a graph of documents. Of course, there are also web apps, etc. And these documents, although the web has tremendously advanced since its inception, still, I mean, largely the web is still a graph of documents meant to for humans to read. And the best proof of that claim is actually the way how we can search the web and access the web, which is basically searching by keywords. A Google search is searching by keywords. And keywords are just words in a document, which proves basically that we still view the web just as documents that humans read. Now, a goal of making the web into a real database would be to make the documents computer readable. Now, of course, I know that a text, a bunch of words is also computer readable, but what I really mean by that is that every web page should basically have an underlying data set that holds the actual information carried by the page in a way that is really database processable, and in a way that we can actually then query this entire web as a database. That's the vision. This is a very old vision. It is already from the 1990s, but it is of course unfulfilled. We don't have that. There are of course many proposals. I mean, this is not my idea. This is a very old idea. There are lots of proposals, lots of competing ideas. Perhaps it is totally naive, totally unrealistic, but it still remains, I think, a nice dream nonetheless. The second unfulfilled dream is that of personal information management. So what we currently have is what people have described as inverse privacy. We have no privacy at all, basically, on the web. Basically, the situation is completely the inverse. Others have our data, and we have no access, except perhaps if we request it, or if we demand it, or if we make laws that actually oblige the other parties to do it. But they will only do it because the law is there. And so, again, the dream is to turn this right. So the basic idea should be that I have my data, and I may let others access some of it. These others could be Facebook, could be the government, could be anything. Now, also this thing is still unfulfilled, of course, but is also slowly turning into a business. There is more and more activity. There are providers coming up who actually provide systems to do this personal information management. There are providers that host so-called pods. A pod is something that you can think of as personal online data, and people put pods that they completely control. There are also ongoing web standardization efforts, for example, the SOLID protocol that somehow specifies how people can demand access to your pod and to to resources of information in your pod. So these are the two unfulfilled dreams, and in our project, we kind of ask the question, can we marry these two? Can we fulfill them? Probably the answer is no, because it's just a small project. But at least, can we do sensible research on these themes? And we make these themes more concrete in the following two main streams in our research, which is first data exchange and second guided link traversal. And please note the very strange letter G that I used there. It's rather Q-shaped. Okay, so let me start with data exchange. Actually, I will mainly talk about data exchange part of this research in this talk. What is data exchange? An abstract setup could be described as follows. There are many agents on the web. They can be personal people, they can be institutions, can be companies, can be governments. And let's talk about two agents in particular. Let's call them Alice and Bob. Alice has a data set, which we will denote by the letter D, and Bob would like to query it. And Alice knows Bob's intentions and grants access to Bob. But Alice will never give her total data set to Bob for various reasons, which we will see shortly, reasons of compatibility, also reasons of privacy. So therefore, Alice is going to apply a schema mapping to her data first. So let me give a little bit more background on these schema mappings. So Bob expects Alice's data to be of a certain nature and also to be structured in some way. Now, of course, Alice's data is going to be structured differently. So that's the first reason why we need some kind of mapping to happen, just for reasons of compatibility. But of course, also, Alice in general does not want Bob to see everything. That will never be the case, I would say. So also for reasons of privacy, there is going to be a mapping to be applied. So you see that these schema mappings can serve both purposes. And so what in effect will happen is that there will be a mediation taking place. So all agents on the web, they will actually have some kind of semantic web agent working for them. And Bob will send a query, which we denote here by the letter Q. Bob sends a query to Alice's web agent. And that agent will spawn a mediator, and that mediator will do the following. Recall that the data set is D and M is the mapping. Well, the mediator will apply the query Q, but not to D itself. I mean, it will apply the query to the mapped data set M of D. That's basically what is going to happen. And Bob is then going to receive the results. That sounds all extremely simple, but there are many issues involved here. And so let me go into some topics that we are researching in this setting. First, a topic is going to be about languages and formats. The second topic is going to be about query rewriting, and the third is going to be about shapes. So let's first talk a bit about languages and formats. So whether you like it or not, I mean, RDF is, for the moment, the customary format for semantic web data. But actually, what I'm going to say here, if you don't like RDF, actually, all the principles that we will talk about is applicable to any other format too. And so Sparkle is then the basic query language that Bob typically will use. But the data D, the data set D that Alice has, it will typically not be in RDF. I mean, it will be in another format. It could be a relational database. It could be just in spreadsheets. It could be scattered around. It could be XML files. It could be JSON data. It could be anything. So the schema mapping will effectively be a mapping. If you view it mathematically, it will be a mapping from the domain of X documents to the range of RDF documents. And so an interesting question is actually, how do we write such schema mappings? Do we just write them in Python, in Java, or can we do better? And indeed, we believe in a language that is called RML. RML is a proposed standard language, which is still in its infancy. I mean, it's ongoing development. It's not at all a standard yet. It is still something in, as I said, in its infancy. The idea of RML, however, is very interesting. I mean, since the dataset D could be in any format X, RML mappings should basically support any query languages, any query language at all, because D has to be accessed in some format, and so you need an appropriate query language for that format. And then the idea is going to be that in RML you specify some rules, declarative rules, that transform those query results into RDF. Now, such rules have been studied extensively in the theory of databases, actually. And so one of our goals actually now is to somehow bring this theory more into practice. So another topic that we are researching is query rewriting. So recall that Bob poses a query queue, and this query will be processed not on the dataset D that Alice has, but actually on a mapped dataset M of D. Yeah? So you see that here. So we have a dataset D. We first map it, M of D, and only to that we apply the query Q. Now there are two options in realizing this. The first is called materialization. I mean, so the mapped data set could be simply materialized and simply could be made available to people who want to query it. And then, of course, there are still many options. I mean, how that querying is going to happen. I mean, is it just going to be an endpoint where people can come with their Sparkle queries, or are you going to allow it to be downloaded, and many other things in between? But that's, let's say, the first scenario is that MD is going to be materialized. Another scenario, however, is that MD is never going to be materialized at all, and that actually Q and M are recompiled, and we call that rewritten, are actually rewritten into a direct mapping M2 that is denoted here by the symbol M2. And so when a query comes, we're actually going to answer it directly on the dataset D by some rewritten query. So how this can be done depends a lot, of course, on the query language that's used in the mapping to access the source data, as well as the query language that the query queue is posed in, and many other considerations. So this is actually quite a rich topic with many intricacies. Another aspect is what I said already a few slides ago about the expected structure of the data. I mean, you can't expect Bob to just issue a query without that he knows anything about Alice's data. I mean, he's going to expect something. He's going to expect at least some structure. Otherwise, he wouldn't know what query to ask. And so a recent idea, not so recent, but relatively recent idea, a schema formalism, has been developed and is called shapes. Yeah. So there is a language proposed by the W3C, which is called Shackle, shape constraint language. And in that language, you can somehow you can formulate some expected structure that you would like to have. An example of a shape, I'm not giving it here in the Shackle syntax, I'm just giving it in English, is like a shape persons that would somehow match any kind of resources that have an email and a first name property, and possibly some friends, provided that these friends have also that shape. Yeah? So such shapes could even be defined recursively. Originally, shapes and this language Shackle, they were originally meant for data validation. So you have RDF data and you want to validate whether they whether this data satisfies structural constraints. But actually, our idea in our research is actually to use it for also for other purposes, for data exchange. So the idea would be then that Bob actually requests a shape. He formulates his expectations of what kind of data he would be able to query, yeah, using a shape. And then there are various questions that we can consider. For example, can Alice's agent automatically generate a mapping? Yeah? Of course, there will still be privacy part of the mapping, and there Alice will have a say. Yeah? But apart from the privacy aspect, you may think of the compatibility aspect to be handled completely automatically. Yeah? So that's one of the aspects that is being investigated. Another question that we are investigating is actually how powerful are such shapes? How powerful are they as a formalism? Yeah? Because we really want to know what you can describe using shapes and what you cannot, given that this is a relatively new technology or a relatively new declarative language, if you want. For example, people have been really confused about how Shackle relates to OWL, which you could call another failed semantic web technology. And so actually our goal is to make Shackle not a failed one and understand it better and clarify its relationship to OWL and confirm or disprove claims that people have been making that Shackle can actually effectively replace OWL. Yeah? Because I will not going to talk about OWL, but people who know about OWL will know that it's really wide adoption and wide use has really never materialized. So this is what I wanted to say about data exchange. I also want to just briefly talk about a second theme of research that we are doing, but I will just spend one slide on it and give even less details than I have done for the rest. And this is querying the World Wide Web. What I mean by Wild Web is, well, until now we have basically talked about pretty controlled data exchange and how you can actually envisage that, how you can structure that, and what are the different aspects in doing that properly. But what about the original vision that I had in the beginning of just querying in the wild? I mean, how can we just query the web as it is? And there's a lot of ongoing research there that we are also doing in our project. We call it guided link traversal, because the idea is that people have data, people have their local data. You could view it as a seed document, but people have lots of links to other agents. And like there is one completely unrealistic way that you could work is as follows. We take all the links in our document, they also point to documents, so we will merge all these documents with our own document. But this has to be done recursively because these linked documents again contain links, which again may hold valuable data. Think of what I said. I mean, in principle, every web page should have an underlying data set that contains the information. So that is completely unrealistic. I mean, you would not be able to do that. And it would also be undesirable because even if you could do that, you would probably not want that because you don't trust everybody's data as much. And there should be a better way to integrate all that information, and that's what we are researching. So our current approach is that agents construct a subweb, and these subweb then have to be reconciled. How this is being done, I mean, I will not go into details here, but the end goal would be that each agent can just Sparkle query a virtual worldwide RDF graph, and moreover that for every agent, this graph is actually different because it will depend on their own subweb construction, but also on the subweb construction of the people they link to. So that is research that's going on, where actually some advanced techniques from knowledge representation in AI are being put to use. So I've already finished. I mean, because basically my goal was not really, maybe it is a little bit different talk than people here are used to, in the sense that I didn't really demonstrate any system or didn't go into any details, because actually my purpose here in this talk, short talk, was just to give you in 20 minutes or less just an overview of what we are doing. Of course, if you're interested, and I can always give you more information and also connect you to the people that are doing this research. I would, however, want to mention also in particular the Vito. Vito is our partner in a use case where we're also trying to prototype many of our research ideas in practice. So they are involved in a project, in a data sharing project run by Domus Medica, which is the union of general practitioners in Flanders. And they are issuing some kind of questionnaire on general citizens' health. And so many partners are interested in this data for research projects or for other purposes. And many citizens are interested in filling these questionnaires together with their general practitioner. And so many of the concepts here that I talked about play a role here. So having your personal data, having it yourself in control, giving people access to things that you want them to know, etc. So yeah, that concludes my talk. I thank you for your attention.
Thank you, Peter. I was muted the whole time. I've been talking for a minute. Thank you, Jan, for the great talk. That was very interesting. So, if people in the audience have questions for Jan, leave your question in the comments on YouTube, and I can ask it to Jan. While we wait for the questions in the comments, Jan, you mentioned the last use case. You're doing a prototype there with Vito, where you can use this technology in a prototype fashion to query the health data of general, well, the surveys filled out by people together with the general practitioners. Does that mean that if I want to know, well, I'm just making stuff up here, but if I want to know, like, are people more stressed out because of Corona now than they were before? That is a query I could launch towards that system, and then that system would spread out over all the different systems of the general practitioners, generate the answer for me, and then bring the result back without me seeing the original data. Is that the concept, or did I misunderstand it?
Yeah, something along these lines. I mean, suppose there is a research project that wants to know about the stress of people, then it can announce it, that it can advertise this project, and people can then actually read about it and say, yeah, okay, I want to, it's fine if they know my stress level, and I will just release my stress level. My web agent will actually not even release my identity. It will just release my stress level. And then, of course, there needs to be some architecture set up to aggregate this information, to collect it, and to use it.
Okay, that's cool. All right, I see another question from Jennifer. She asks, what do you think will come first, a legal framework or solve the problems that are there to be able to do this?
That's a difficult question. I'm not sure. I think these are two things that both have to happen, in a sense. But of course, the legal frameworks, like I'm not sure if Jennifer is referring to, for example, GDPR or things like that. But it is true that GDPR, in a sense, we were forced to. I mean, the EU was basically forced to issue that kind of laws because we have no privacy. Yeah? And so, in a sense, indeed, I mean, if we would be able to set up personal information management really in the right way, then in a sense, your personal data would be just any other valuable asset that goes around in the market. I mean, some people are actually thinking of that in that sense. But in general, of course, legal and technology always have to go hand in hand. And I actually, to be honest, I don't really feel an expert on that kind of questions, Jennifer. Sorry.
Okay, that's cool. Then another question or moral remark. Sabri Skiri, I hope I pronounce your name correctly. He says, like, hey, I'm interested in getting in touch with the research team. We use Shackle for GDPR compliance on data access management. So maybe Jan, maybe you said it, but how exactly can he contact you? Or
Yes, so my email address was on the first slide. I don't know whether, but Chris can probably share my email address.
Yeah, I'll make sure that I share it again. Sabri, I'll put it here on the chat, so you can find it again. All right, are there other questions for Jan? No, I think that's it. Jan, thank you very much for your talk. It was
Thank you.
it was very interesting. And then I guess now we can go to the next speaker. Thank you very much, Jan.
Bye.
Let me. Yeah, sorry, he said my pleasure, and then I kicked him off the stream. Next speaker is Geert and Sebastien. Geert, I'm adding. Sorry, I'm mixing it up. It's Geert and Jan. Apologies. Geert and Jan from Python Predictions. You're both muted, so don't make the same mistake as I did. Geert, you're still muted. So I would say, yeah, kick it off. Thank you.
Awesome. So hi, welcome everyone. I'm happy that I can be here. So in the next 20 minutes, I'm going to talk about Cobra, what it is, why did we open source it, and there'll be some small hands-on demo at the end. So stay tuned. Now, just a little before we start, there is a small slide about myself. My name is Jan Benishek, and I'm a data scientist / data engineer at Python Predictions, where Since
Hey,
2006,
hey,
we do.
Jan, sorry to interrupt you. You're not sharing your slides yet,
Oh no, what
but that's
happened?
fine. I'll add them the moment you add them,
Oh
and then you
yes, I
can
forgot to
continue.
click the button.
Yeah,
Thanks.
that's cool.
Is it better
Uh,
now?
it's coming, and it's
It's
there. Yeah,
coming.
go ahead. Yeah.
Awesome. Thank you. So as I was saying, I was talking about us as a Python predictions. We do data science since 2006, and we try to help business to make better data-driven decisions. But now let's come back to Cobra. I promise all of you that after this talk, you all will be as brave and as skillful as this kid with Cobra. So let's dive in. I want to first start with actually what Cobra is, to make it clear. Cobra is Cobra is not some kind of auto ML. Cobra is not deep learning library. Cobra is not a versioning system. Cobra is a Python package which actually lets you build data science models quickly, and these models are extremely well interpretable. So I'm going to elaborate on that later on the next slides. But it's good to set up the stage to understand what actually Cobra means and what Cobra actually does. Now, before we go into the methodology, I want to talk about actually why Cobra, why we built Cobra, why we actually be bothered with all this. And there are actually 3 points here. The first is what I call coverage, because we as a consultants, we do many projects with many clients, and we saw that the majority, or at least many of the projects, are very similar in a sense that it's some kind of classification problem. Whether it's churn, whether it's cross sell, upsell prediction, whether it's burnout prediction. It always boils down to some kind of binary classification. So then, okay, we realized, okay, I mean, we keep doing similar projects. Perhaps we should automate this. So, and if you automate something, you want to start, with a bulk. You want to start with a apples which you can reach. And the second reason we saw that actually is if you do lots of projects which are actually very very similar, and you make the effort and you hire smart data scientists, then actually they would keep doing the same projects. And I think the worst thing you want is to let your smart and experienced people keep doing the same work. Okay, that actually brings us to the second point: automation. Because assuming we have like this nice Python library which lets you build models, this actually means that we can build the models, quickly in a fast and automated fashion. So actually, this leaves time for more. I want to say fun work, but okay, I'm gonna say fun work because somebody maybe wants to spend more time exploring the newest random forest. Somebody wants to spend more time with the business. Somebody wants to spend more time with setting up experiments. And basically, having the model building automated leaves your hands to something else, something more, which then actually leads us to the third reason why we made Cobra, and that's availability. Because if you have a package which you can trust and which can build model quickly, then this actually becomes very much available. It doesn't cost a fortune to build a model, so it's available for small customers. But also, since it's constrained, the model building, you can also let with confidence your junior data scientists build these models. So you can build more models, clients are happier, and basically everybody's happy. So we think that automation is the key, and that's why we built Cobra, while keeping in mind that every model we build has to be interpretable and should have at least sufficient performance. So I hope that's clear. And this actually brings us to the next question, and actually that's actually why we open source Cobra. And we had lots of discussions about it, and I think we arrived to two reasons. The first reason is that we somehow feel that we are part of community. Belgium is a small country, so we feel like sharing is caring, as we say. We feel like giving back is important because we are not lone wolves, somewhere in the desert. We are here with other companies, with other friends and colleagues. So we want to, also give something back, which also means we want to bit, grow together. Because if we publish something, perhaps there are some bugs, perhaps there is something to be improved. So we actually want to also get this feedback and help each other grow. And the second reason why we actually open sourced Cobra was transparency. And actually that goes, to use fancy data science lingo, that relationship is bi-directional, which means that it goes towards our clients, because we saw that clients, um, you will never use something which you do not trust. If me as a consultant, I'm going to go to my client and I'm going to give him or her like a black box, they will not like it, because they don't know what's inside, they don't know what's happening. So basically, open sourcing Cobra shows us what we do, shows how we do it, and we feel that it actually brings more trust to the relationship. But of course, this also works towards us in the sense that, for example, for potential applicants or for other people outside Python prediction, they can see what we do, they can see how we work, and we could actually attract the right talent. So actually, these are the two reasons why we open sourced Cobra. Now I'm gonna go briefly over the four main parts in Cobra, and actually explain you what they do, what they contain, and after we will jump on the hands-on. Basically, Cobra consists of four parts. So it's when you build a model, there is a data pre-processing, feature pre-selection, there is model building, and of course, finally, evaluation. Now the methodology behind it's actually nothing new. Actually, my boss Gert and Wouter, they built this methodology. They've applied it over in the past 15 years at many clients over many domains. So it's actually it went through all the battles and it survived. So we are quite confident that the methodology itself it's sound and it delivers what it promises. Now, of course, it's always work in progress, which means that we are always trying to add new features, maybe review the methodology, or for example now publishing it on GitHub. So it's always ongoing. It's a living thing. It's never going to be perfect, but we are trying to make it as good as we can. And last but not least, I have to mention that although here my face is here now, actually Cobra actually was built by many people, by many of my predecessors. So it's really like a team effort. It's a big collaboration, and so it's it's almost like a family package, which is now finally outside. All right, so let's start with the first part, and it's data pre-processing. Now, in the first part, there are actually 5 main bullet points. And actually, a lot is happening here. And actually, this is the key. This is the key of the Cobra methodology. So in the first part, what we do, we split the data into train, selection, and validation, where you would always train the model on the train set, then you evaluate it on the selection, and then at the end you would use a validation set to finally validate your data set. We also bin continuous variables into intervals. We replace missing values. It's an obvious one. We regroup categorical variables because, for example, you can have a feature which is many variables. So perhaps you wanna put them together. And lastly, we target encode bins and categories. Now, to elaborate on this is something which we use and which is also the core part of Cobra, and it's something we call pig. Okay, but not the animal, but actually predictor insights graphs. Now, there is a dummy data where in this data set there are customers, or I guess just people, and it's a binary problem where 1 means that your salary is more than $50,000 per year, and so 0 is that your salary is under 50,000 euros per year. So that's what we call the incidence. Then in this case we use variable age, and we bin it into certain bins. So, for example, in this case, at the left side, you can see that in this population, the 12% of the people are actually with age between 17 and 22. So you can see the kind of distribution of age across your data set. And then the orange line shows you the incidence. So number of people who earn more than $50,000 per year. And you can actually, it's very simple. You can see actually how as people grow older, they are likely to earn more, right? I mean, it makes sense. It's very simple, but actually, if you show this to somebody without any hard quantitative background, it's very intuitive. It's easy to understand. It helps to understand what's the model doing, how it's deciding. It lets you very easily open the box and look into it. Now, there is a bit more behind this, and especially we also get the discussion about the target replacement. So Gerd, who is also now here, he wrote an excellent article where he actually digs more into the whys and into the more of the technical reasons. So because unfortunately I have only 20 minutes, so there is this nice article which you can follow and read to read more about incidence replacement. The next step, feature pre-selection. Now, these days, every company has or many companies have a huge database with many columns which you can use to build models. But now you have two choices. You can just take all the variables and dump them into a model, which would work, but then it's somehow difficult to obtain interpretable results. So now what we do here, we take all the model, we take all the features, and we pre-select, I don't know, top 50, top 100, doesn't matter, features which are actually mostly correlated with the target. And we actually use AUC as a ranking, and then we select top N features based on that. So having pre-selected features, we continue to build our models, which is the the juicy part of data science. So where basically Cobra builds multiple models in a forward fashion, and then gives you comparison of the models, shows you feature importance, etc. It does all by itself for you. So you just click a button and you get the results. And of course, the last step, which is the evaluation, because of course you want to know how well, how awesome model you've built. So it shows you, either the scalar metrics such as AUC or accuracy, but also evaluation plots such as lift or confusion matrix. And of course, you get the predictor incidence graphs. So this was like a brief overview of what's in Cobra, but I hope that now it's a bit time to get our hands dirty and a bit see inside and see actually what's happening and how we can see all this working in practice. So let's be as brave as this dog and jump in. So I'm going to switch to my Visual Studio Code. I hope the letters are all big enough. You can all notice I have a dark background because I'm very serious about my work. So Cobra. There is official GitHub repo where you can click and find all the code, documentation, etc. There is also I put a link to my documentation where you can click on the link, and you see all this nicely written and described. And in order to use Cobra, you just magically do pip install, and voila, Cobra is installed. And for our purposes, I use like a very simple data set. As I said, survey of adults and their earnings, where 1 means income over 50,000 and 0 means income below 50,000. Okay, let's dig in. So we start with the usual imports, nothing interesting there, and then we continue. We load the data again. Nothing groundbreaking. So you can have a quick look for features such as age. There is a gender. And then, of course, at the end, target 0 or 1. So we will start with the pre-processing, as I said. So, and again, to remind you, we split the data set, we bin continuous variables, we replace the missing values, we regroup categories, and we do the target replacement. So we start by initializing the preprocessor class, which basically you can give it a bunch of parameters such as how many bins you want, etc. And then we gonna go and say Cobra, okay, I want to split my data into 3 parts, into train, selection, and validation. So we just do that. And if we again inspect our data set, we see it's the same. But now we have one extra column here with split, which indicates train, selection, or validation. Okay, very simple. Then we continue to the actual preprocessing. So of course we need to tell Cobra what are our continuous variables, what are our discrete variables, which we've defined before. You noticed that actually it follows the same verb logic as sklearn, in the sense that we use always fit and transform. So people know it. So here we fit and then transform the data, which means that, for example, in the fit, it bins the continuous variables into intervals and then applies it on the data set. So once all this actually runs through, we can again have a look at the data set, and we have a bunch of new columns here. So let's have a look. Let's, for example, take age as example. So age is here, as before, as a continuous variable. Okay, all good there. Now we have age again with the suffix bin, and we see that the variable is age, but it's binned into intervals. Okay, very nice. That's what you wanted. And you get the age third time as a ENC encoded, where we take the bin, and per the bin we calculate average incidence, so the average target from the train set. So for example, here the average target in this age bin is 0.28. But of course, it's a bit more complex than that. There is some kind of smoothing behind the place, so it's not a simple average, but at least to get the idea. And of course, now we will do the modeling and the analysis on the encoded data. That's important. But okay, now let's continue. We've prepared our model, our data, so that we can start with pre-selection. And here I'm going to say Cobra, okay, here are the train set, the selection set, and I want all the columns which have AUC of at least 0.53. And I also want to only select those where the difference of AUC between train and selection is at least bigger than 5%, because otherwise we risk overfitting. Okay, so we do that, and we get like this beautiful plot with univariate quality of predictors, where we see, if we have a look, there's AOC train and AOC selection bars. So we see that the relationship appears to be the strongest univariate feature. So we can inspect this relationship, occupation, education. Cool, makes sense. But we also get this correlation matrix, because sometimes you want to look at your columns and okay, maybe drop some which are heavily correlated with some other variables. And if you look here, for example, education number of years is correlated with education, which makes sense. But okay, cool. So now let's proceed. Now we go to the modeling part, to the juicy part of data science. And so now basically there is a method forward feature selection. I'm going to say I don't want more than 30 predictors. Fair enough. And then again, I'm going to do fit on the train set, and voila, that's basically it. I get this beautiful plot where I can actually see what's happening. So let's look a bit closer here. This shows us the AUC on train, selection, and validation. And let's see. So the model actually starts looking for the let's call most significant or most important variables, and the first it found was relationship. Okay, so it takes the variable relationship, takes it into the model, and then keeps searching. All right. The second most important variable for the model was education. Okay. Now we see that the AUC actually jumped from 0.78 to 0.85. Not bad. So adds second feature and continues. And then of course the third most important feature is age, and the AUC bumped to what, 0.87. So now we have model with three variables, and like this it continues and it continues until it stops. But of course, you can see, or that at some point adding new variables will not bring you additional performance. So I'm gonna say here 1, 2, 3, 4, 5. Let's say I'm gonna be greedy and I'm gonna say after 5 variables I have a great model. Okay, so I'm gonna do, and I say I want a model which with 5 variables. But as you all know, because you're all smart people, that Python starts with 0, so we have to tell that the number is actually 4. We choose the final model, and we can look at its performance. At its variable importance. Now, the variable importance is basically a correlation between the scores and the variable itself. So, for example, here the relationship, the correlation between the relationship, the encoded relationship with the scores is over 0.7, which is pretty strong. And again, it's very simple to explain this to, let's say, your project manager, because you say correlation, these two variables are correlating together, makes sense. Everybody's happy. All right, so I've built a model. I've chosen this one because that one is the prettiest, I think. And I go to evaluation. So let's see how well we are doing. So we've got of course, the ground truth. We calculate the predictions from the model class, and we fit the evaluator. So the scalar metrics. Let's see. AUC of 0.88, not bad. Lift at 5%, 3.56, not bad. In like 10 minutes, the model is quite good. I'm happy here. And then, of course, as I mentioned, you get some additional graphics such as ROC curve. There is confusion matrix, which you can explore. There are cumulative gains. There are a few more. There is cumulative lift, and there is cumulative response graph. So you have all these graphs which you can inspect and see how well your model is actually behaving. And then this brings us to the last part, to the big tables. Again, not the animals, but predictor insight graphs. This is the one I showed you on the slides, where you remember we bin the features into bins, and then we laid over with average incidents per bin, and we obtain this beautiful graph. Of course, here there is a function for it, so you can say, I want from the data, I want this variable, and I want to give it specific order, and voila. But of course, sometimes you maybe want different colors, or you want to tweak one label a little bit, and this tends to be a bit difficult, doing only with Python. So usually we also export this, as a table, such as this one. And actually, you can recreate this graph just from this data. And we sometimes, I asked, or I shouldn't tell, but had asked it in Excel. So then you can do data science in Excel. But it works. And of course, so lastly, we build the model, we defend it in front of the business. Everybody's happy, everybody understands it. So the last step is actually industrialization. And actually here, behind what Cobra does, it actually outputs well, we call it a pipeline in a JSON file, which is a JSON which contains a bunch of metadata and all the pre-processing steps which we have taken. So actually, when you put a model to production and you want to score it, you would load this JSON file, and you can easily again pre-process the new data before you score them. So for example, we talked about the age. So in the JSON file, I'm going to look up the age, and I'm going to find the bins. So I can bin it, and I can replace it with the incidents. And actually, I have the data ready for modeling. So it's also pretty simple, not only to build models, but also to industrialize them. And I believe that concludes my hands-on. So I think that is all. And now, if you have any questions, shoot.
All right, thanks, Jan. While we're waiting for questions in the audience, I have a question maybe for you or for Geert. Sorry, I'm having a cold.
No worries.
I guess what I see here, and by the way, I know your organization for quite a while, so I recognize a lot of what you say here,
Yeah.
which is good, right? To be clear. Does this mean that when you have a library like Cobra and you go to your clients, this enables you to speed up a lot of the data science projects that you do, plus gives clients more insight? Why did you build this, basically? That's the question. Why don't you just take scikit-learn off the shelf and do it from there? Why did you? I think I know the answer, right? But I want to hear
Yeah,
from you.
yeah.
Why did you build it? Yeah.
Yeah. No, because you see, there are some steps, such as the predictor insights graphs, which are not available anywhere else. So we thought that this is actually, additional value for the clients, and it helps them understand the models better. Because with scikit you can get models easily, but they are not always interpretable. So Cobra was built with interpretability in mind. So it might be simple sometimes, but it works very well. And again, if it's simple, people understand it, and if they understand it, they will use it. So
Yeah.
this was the main reason why we built Cobra in this way.
Okay. Yeah. And I think what I especially like about this is that I'm a data engineer myself, so I know just enough data science to do damage, but I don't know enough that if you give me scikit-learn, I can train a model, but I'm probably doing it wrong. And what I like a lot about what you're offering more of a framework, like a step-by-step, like first do this, then do that,
Yeah,
and
yeah,
look at the graphs, try to make sense of what you're doing before you go back to business and say, hey, I found a model with a high score. No, like you guide, let's say more novices like me, you guide me through the process. So I
yeah,
like that a lot
absolutely.
about what you
Yeah.
offer. Yeah.
Absolutely, that's great because we also saw that with some juniors, it's so easy for them to take Cobra, go and build models at clients. We know it's gonna work. It guides you. There are some constraints on the side, but it still leaves some room for creativity. So
Yeah.
this
No,
works
super
pretty
cool.
well for us.
All right. I'll look at there are some questions by now. So
Yeah, yeah.
Sabri asks, for the correlation between features and the results, is it really a correlation or the contribution of the feature to the results, like in SHAP or Lime?
Between the results, I think it's a correlation there because you get a score which is a continuous variable, and the variable itself which is encoded, so it's also continuous. So we calculate the correlation between these two. But we are
Okay.
now,
Yeah,
yeah. But
yeah. I want
Gert,
to
if
add
you
to
have,
it. Yeah, I want to add to
please
that a
go.
little bit. We've had an amazing amount of discussions about this one. How do you calculate variable importance? And you can tackle it from very different angles. And basically, what we feel makes most sense for the business is how important is this variable in the end result. And so we don't really want to take into account, for example, if the first variable is really important and the second one is equally important but covers the same information. We want to show to the business that actually they could be intertradable. You could leave one out and take the other one. They have an equally large correlation with the end result. And so that's why we think the correlation is indeed a better measure. And as Hansa said, indeed, if your features are all continuous because they're target encoded, and your prediction, your probability is continuous, then you can calculate a correlation. We've done some variations on this, but it's the easy. We've always asked ourselves, if we add complexity, it should also add value. And this is probably, we only make it a little bit more complex if it really adds more value. And this is where we said no, correlation is the easiest one to understand. and is enough actually for business.
All right.
Yeah,
Thank you.
thanks.
Then Raf has a quick question. Only binary classifiers? Question mark.
Yes, at this moment it's only binary classifiers, because as I said, the majority of the problems are some sort of binary classification. So we say let's start from there. But of course, continuous ones are on the horizon. So one day Cobra will grow.
Okay.
Yeah, to make it concrete, the exact same concepts apply to continuous targets. So we use it internally for a long time. For example, there's a burnout case that we have on SlideShare as well, where we use it for a continuous target, the number of days that people will be absent, and it's exactly the same methodology that can be applied, but it's not yet in the open source part.
Okay, cool. And then Edmund asks, hi Geert and Jan, thanks for the presentation and for making Cobra an open source software. Question, what is Cobra's unique selling point compared to Microsoft Azure ML Studio, which has a UI and for providing similar functionality?
Okay, good question. I think for us it's the simplicity and the fact that it builds or white box models. So it's simple, it's fast, and it builds models which you can easily understand. So we think that this is the main selling point. I don't know if you want to add something else.
No, I think the fact that it's easily integratable, since it's all in Python, is something that adds. We've seen us. We don't need a lot of dependencies. We don't have a lot of dependencies for integrating it in a large client environment. So we usually set it up quite fast. But to be completely honest, we've always been writing code. We've always been writing code. So we haven't used a lot of the other pre-packaged stuff, because usually people pre-package it a little bit differently than what you exactly want, and that's why we've written our own. And this one, obviously, you can customize it.
All right, thank you. Then Wim asks, thanks for the nice presentation. Is the AUC under the ROC curve you use? Is it the AOC under the ROC curve you use? I don't know if that's a real sentence, but I don't know if you see the question. Do you also use it for highly imbalanced data, or do you also consider other measures such as the AUC for the PR curve?
Let's see. I mean, we do use it also for more skewed data sets, and this is the regular AUC. It's the plain AUC. But if we feel like it's highly skewed, then we probably wouldn't use Cobra, because then it's a bit specific case. It's not your average classification. So then we would have to develop some more custom solution.
Yeah, the
Because
only
of course,
AUC in the package
yeah.
is indeed the AUC under the ROC curve. So that's right. That's the only one that's packaged, but it tends to be reasonably good for the type of questions that we're aiming to solve, that we typically solve in Belgium. So we're looking at data sets from tens of thousands of observations, or even thousands of observations, to millions of observations. And in terms of skewness of the target, usually 1% to 10%, it holds up fine. So you need to go to extreme cases for it to break.
Yeah, indeed. Again, Cobra doesn't work. There are cases where you wouldn't use Cobra, which are maybe too difficult or too exotic. But again, Cobra covers the bulk of the classification where we can easily use it.
We consider it the quick starting point, not a solution that covers everything, but a quick starting point. If you throw it in there, you'll quickly have a reasonable solution.
Okay, thank you. And then finally, Raf doesn't have a real question, but just a remark that he has a great multi-classifier problem laying around, Jan. So probably, I don't know, maybe this is an inside joke or something, but he'll get in touch, I guess.
I hope so.
All right, Jan and Geert, thank you very much. It was super insightful, and it's definitely, and I swear to God, it's on my backlog to try out, because I really want to try. Like, I know I hack too much in scikit-learn, so I really want to try this out. Thank you very much.
Perfect. Thank you.
All right.
You're welcome.
Bye. All right. Let's see. So let's add the people from BioStrand to the stream. So it's add to stream Derek and Sebastien. Welcome. Welcome, gentlemen. So last but not least, the floor is yours. Please introduce us into the wonderful world of biostrand and genetics engineering and genetics data science.
All right, let me share my screen. Okay. Wait a minute. Okay. Wait. Oops.
Yeah, it's coming. All right, it's there.
Let
All
me
right.
show you. Okay. Do you see the presentation right now? Okay, so first of all, I would like to say that I'm quite grateful to participate in this Data Science Leuven webinar. My name is Sébastien Lemarle. I'm currently a data scientist at Biostrand, and I will now present you how to overcome hurdles in omic analysis using Biostrand's method. And I will present part of this talk, but part of the talk will also be presented by the CTO and co-founder of Biostrand, Dirk. So, well, this is a webinar on data science, and I want to put a bit of context on how omics data analysis fits into this discipline. So in biology, well, biological functions are usually mediated through macromolecules. So these macromolecules are deoxyribonucleic acids, ribonucleic acids, or protein most of the time when we are speaking about this biological molecule. And so if you want to see where it fits within the cell, that is indeed the unit of biological, of biology, of life itself. Well, here we have an eukaryote cell. This eukaryote cell contains a nucleus. And within that nucleus, you have your genetic materials, which is exemplified as a chromosome here. And that chromosome is actually constituted of a strand of DNA. And so here you can recognize that strand of DNA that is composed of a double helix. And within that double helix, you have the sequence of nucleic bases. And so this encompasses the genetic code. And basically, the information that you find in this macromolecule are stored as sequence of monomer, which are basically the single units, the small molecules that appear sequentially in these different molecules. So it's quite straightforward to see that from a DNA sequence. For protein sequence, which have complex folding, it's usually difficult to see that. So here you have a representation of such a molecules where you see the individual's atoms, which are binded to each other. And actually, within this mess, if we represent this macromolecule with a cartoon representations, we can see indeed that it forms some kind of strand. And we can have also another kind of representations where we do see the different amino acids within the sequence that are coming one following another. And so basically, in omics data analysis, we deal with sequence. So what are the kind of sequence that you encounter in omic analysis? Well, this sequence can be either sequence of nucleic bases, where you have indeed 4 kind of character, or you can have protein sequence that mostly feature 20 character. So basically, in order to compare one sequence to another to see what are the ones that are the closest related to one, we perform some kind of alignment of the sequence. We call that sequence alignment, and this is at the very basis of any kind of analysis. And it's especially important for unstructured data where you do not have any kind of annotations. So you have one sequence and you want to know exactly where it comes from, then you need to compare it to other sequence from which you do have the corresponding data. And this problem of alignment is usually solved through dynamic programming algorithms, which are algorithms that have complexity that scales with the length of the sequence. Also, well, omics data is textual data, but traditional text analytics methods, NLP methods, are mostly useless in this situation because it's not natural language. Okay, so here we need to come up with different techniques from what is usually encountered in a data science project involving textual data. And so, well, the kind of analysis that can be done start first from the very experiment that is called a sequence, sequencing. Well, in the current context of coronavirus, you should be quite familiar with sequencing, because it basically amounts to reconstituting the sequence from an experiment. And so when you do this kind of sequencing, you never end up with the whole strand and the whole sequence itself. You can only get part of it. So basically, you get some short reads, and these short reads must be aligned next to another, sometimes with respect to a reference genome sequence that are not necessarily the same, but can be used for alignment. And then you collapse all of that, and you get your merged sequence, which is then assembled. And then from then on, you can do any kind of analysis, like expression analysis, etc. And one of the most interesting analyses that we can do, which is particularly important in the current context of the pandemic, is variant calling. Basically, within a set of sequence, what are the groups that are indeed alike, where the variation are minimal in between different of them, and what are the groups that are sufficiently different from which you can have different kind of functions, like, for example, resistance to a corresponding antibody. So yeah, in a nutshell, this is at the very basics on any kind of omics analysis. And there are different orders that occur in this field, actually. So the most important one is that data size is growing in a fast rate and basically outrun computer powers. That's one of the main problems that is coming now, because computer power is not scaling as fast as the data. So that's a problem. Another problem is the lack of integration between silos of different domains with specific information. So basically, well, these domains tend to be isolated quite from each other, and it's usually quite hard to link them together. Some of them are actually making that effort, but it's always come down to having a group domain without any connections to other, and that can be problematic. And well, this leads to a substantial amount of knowledge and results as well that remain untapped, and from which we cannot actually get any new knowledge. And also, this leads to a disparate tool environment. So basically, there is a large variety of tools that perform omics analysis, but most of them are not compatible with each other. So you need to be well careful when you do your analysis to pick up the right one from which you will be able to perform your own analysis. And this is exactly where BioStrand fits in its philosophy. So basically, the philosophy of BioStrand is to go from dynamic programming and also heuristic principles that are used for this kind of analysis, and to go from that to an indexing principle that is roughly the same as what Google is using for its search engine. So basically, sequence data assembly analysis goes from NPR complexity to polynomial tractable complexity, which make it more scalable. And also, well, this indexing technology is using sequence feature incorporated in IFT. So I will discuss soon what are IFT, but you must understand that they are the core of the indexing solutions, and at the basis of any kind of analysis that we can do at the genomic and proteomic level. And so we no longer rely on this dynamical programming and heuristics as a first step. So it's a change in paradigm, because we are completely moving away from that. So yeah. So basically, what are these IFTs? So first, we need to consider a IFT, a single IFT, as a data object. So it's not exactly a string. It's an object that contains information and that links DNA, RNA, and proteins all together at all the levels. And each IF contains information on position, function, and structure, as well as encompass a signature sequence that can be retrieved within a protein sequence or a DNA sequence, etc. And when you take all of that together, you bring all the IF together, you basically create a knowledge graph that can link the different aspects all together, and it links all domain and all the species are included within that analysis. So to understand a bit more the principle behind that, you start from a sequence, let's say a protein sequence, and using the biostrand parser, this sequence is transformed no longer as a sequence of different amino acids, but as a sequence of if patterns where the if are highly structured substring of the main sequence, as you can see here. And so they are binded together, and basically any kind of analysis can be done no longer considering the individual amino acid as its own in dynamical programming, but only considering the highly structured if patterns. We do have a small schematical representation of such an analysis where two different sequences share a common part up to that point. So here you have a sequence of if that are identical between the two. There may be some variation, some small variation inside that set, but the highly structured part remains. And then it's split into different segments that are highly different from each other and may differ in function. And so, yeah, basically, this is the main principle behind the biostrand solution. So, relative to heuristics that is usually used in omics analysis, most of these heuristics relies on K-mers, which are elements that may look at first similar to if patterns, but are quite different. So basically, if we have one initial segment of DNA in your experiment and you want to sequence it, you never sequence the whole sequence. Instead, you will have the short reads, as I said, which are basically small strands that may actually contain part of the initial sequence, and they may overlap. And from these reads, well, they can align like this, and by collapsing this alignment, you can retrieve the initial segment, but most of the time, you don't know that in the experiment. And then, in order to perform that analysis, you need to align them. And I must say that here, this is a very small example, but most of the time, the short reads are actually much longer than what you see here. And the problem is that because they are long, dynamical programming becomes difficult, mostly if you have quite a lot of data. You cannot use that because it do not scale. So one of the heuristics that has been proposed is that instead of relying on the short reads and to align them, we create K-mers, like formers, that are basically shorter substrings that are much easier to align. And so you decrease the complexity of the alignment, for example, here, by having only K-mers of length 4, so 4 mers, you basically reduce quite a lot in the difficulty of doing the alignment. But on the other hand, you end up with quite a lot of these K-mers. And that's one of the problems with the K-mers, is that while they are used indeed to decrease the complexity of the alignment, well, they tend to increase quite drastically with the size of the data. I must say here that these Schema are basically obtained by using a sliding window here. So basically here we have one Schema, then we have another one here, etc., etc. And so you get this whole set, and you can remove duplicates that you usually get in a big data set. And so these are basically small strings, which looks very similar to if patterns, but they are different. Why are they different? Well, Schemers are information lengths. They are just strings of fixed length. On the other hand, ifs, as I said, carry information at multiple levels. They have no fixed length, even though they are quite short. And the most important part is that they constitute a finite set. So basically, Schemers scale up with the size of your data set, where if patterns constitute a finite dictionary. All of them are pre-computed, and they can be considered as intrinsic feature of the sequence due to the fact that they carry information. And this leads up to a drastic reduction of search space when you are indeed looking up for similar sequence, when you want to map this sequence to other one, etc. Basically, any kind of analysis that you want to do in omics. So now I will leave the discussion to Dirk.
Thank you very much, Sebastian, and thank you also to explain our HIFT-based methodology. And based on our indexing technology, we can build different type of applications. And I will shortly review this. So one is our retrieve and relate. It's a kind of sequencer searcher, right, where you look for similar sequences, both at the DNA, RNA, and amino acid level at once. The next is our variant analyzer, so to look for mutations, to look for variations, and next is indeed our AI platform. So let's first look, give you a glimpse on indeed our retrieve and relate application. That is here, at this moment, it's running on an AWS platform, so it's really relatively straightforward. So you can just paste the sequence, and immediately you can see all the results that reside in all the different databases, again, from the DNA, RNA, and amino acid level on. And further, you can drill down in several views. We have called it the list view, the explorer view, so really slice and dice your data. And then also a kind of alignment view, so where you really could see how well all these sequences are aligned. So that's a short review of our retrieve and relate application. Next, I will show you an example of how we are looking for variations. And here, well, it's very actual at this moment, looking at all the variations of the SARS coronavirus. And so we have taken around 1 million of this SARS coronavirus variants and made a graph. And you see that on the left side of this slide. So you can see this as a kind of different lanes, where, for instance, some of these lanes are referring to bats, where the coronavirus is in the bats, or in hoofed mammals, or in humans. You see the overlapping parts of all these strains. And what is very, very specific is that some of these HIF patterns are only unique for the coronavirus. So for no other virus, just for the coronavirus. In the middle part of this slide, there you see when we have taken 450,000 SARS coronavirus spike glycoprotein sequences, and with all the variations, and here we built a kind of consensus reference. So all the small dots are the individual HIF patterns. You can immediately, they are collapsing, and then you have a kind of, let's say, reference, the basic backbone of the coronavirus. And also associated with this different HIF patterns are, for instance, different type of metadata, like geographical location. And so that means also that you can immediately see or filter, if you want, where certain variants of the coronavirus are coming from. Further, we can even zoom down to a much more detailed level at the individual HIF patterns, see what are the variations between the different strains, and again, look further into detail to several related metadata. So you really can, it's a multi-scale analysis model in one single, call it box, based on that indexing principle. Next, one of the most important tasks in omics data analysis is indeed clustering. And what you see here is a specific example where we cluster sequences of the highly variable domain of the immunoglobulins against different germlines. And what is really interesting to notice is that we don't need a training model to do this task. Okay? All this network is really easily built based on the pre-computed features of these HIF patterns. And once you have that graph, let's say, then the clustering is an easy step from here on with less computational power that's necessary. So in the next slide, I will just summarize, let's say, how we tackle the different hurdles in the current omic data analysis, and they are the scalability issues, the disparate environments where you store DNA, RNA, and amino acids, let's say, in different silos. So there is no real integration of that data. We are solving this based on our indexing principle, based on this small HIF patterns with this extra set of features. And on top of this indexing principle, we built projects like Retrieve and Relate to look for similar sequences or variants, and even go within our, let's say, AI platform, we go from the syntactical level, so just the, let's say, combinations of letters to more the structural based analysis, so structural biology. So what is the take home message? Is that if you look at bioinformatics, then let's say it started all around the 80s, where they came up with this dynamic programming. It was very precise, but it was slow and indeed not scalable. But in the 80s, well, there was not so much omics data, so that was fine. So around the year 2000, then they came up with some heuristics, called this kind of shortcuts to keep in pace with the growing data. Well, they had good quality, for instance, for alignment. It was fast, but it was not scalable. And that's at least the current state of the art. And so there we made the change to use this HIFT patterns, where we have good quality of alignment, but it's super fast and highly scalable. And also important is versatile. So the fact that you can look from DNA, RNA, and amino acid level, let's say in one box, makes it very versatile. So again, we are very pleased that we could present our technology, especially for this audience. We are still growing, so we're also looking for, let's say, data engineers, and we are very thankful also to Data-Minded, because they helped us to build up the platform in AWS. Thanks a lot.
All right. Thank you. Thank you very much, Dirk and Sebastian. So let's see if there are already questions. I guess not. While we wait for the questions to come in, maybe, and I don't know if you can share that, but Dirk, can you give me, or Sebastian, can you give me a rough idea of, I know this is a lot of data that you're processing, but are we talking about megabytes of data, gigabytes, terabytes? Can you give me some figures about the scale of data sets that you have in front of you?
Well, it depends exactly on the task as such. For now, we use a small data set that are from 1 gigabytes to a tenth of gigabytes. On the other hand, you have public databases, and some of them are quite large. So I don't exactly remember what are the one. Maybe you have some of them, Dirk?
Yes, so let's say on our AWS platform, we have around 300 million sequences already indexed. And so that's indeed in the numbers of the terabytes, of course. But what you definitely see is that with omics data, it becomes really gigantic. So people are used to work with hundreds of terabytes of data. So that's why, this type of approach is very important, so that you can really scale with the data.
One of the most important points is that the sequencing technology is becoming more and more accessible, and it's become also more and more important to perform that. So, for example, with the current context of the coronavirus, it's extremely important to sequence, and so you have now the antigenic test that are indeed used to have the sequence, and this is exactly how we realized that they could have variant with from specific locations that are actually growing bigger and bigger. Of course, it's a small example, but it's becoming more and more important. And also now with the new era of the mRNA-based vaccine, it's extremely more important to have access to that. And the search, the current search engine that's the product is currently using public data sets, but another important part is that the clients can indeed put their own data, private data here, and from there we don't know exactly what are the sites, because by definition they are private.
Yeah. Okay. Cool. Thank you. There's two more questions in the chat. First from Istvan. Istvan asks, hey, you mentioned clustering a couple of slides ago. What clustering method is typically used on this type of data?
Well, here for the clustering, basically we perform a pairwise association of sequence based on how much if they share. And basically you can build a network on that, and using a community detection algorithm such as Leuven, you can perform some clusterings based on that. And of course, there is other way you can map out to reference, and this reference can be used indeed for to help your clustering.
Okay, thank you. Edmund asks, hey, thanks for this. I see you using a lot of graphs for representing the sequences and relationships. Did you have to build your own graph software, or did you use something on the market like Neo4j?
Yeah, so, well, it's a very interesting question, and you see it's call it a graph-based method. At this moment, we are able to store, let's say, our HIFT patterns, and also that network is connected in, let's say, a direct indexing table, call it in that way. But of course, we are also looking to graph-based approaches. So, like for instance, the one who's asking the question, like Neo4j is such an example. Definitely.
Okay. All right, thank you. One more question from Christophe. He asks, who are your main competitors?
Well, yeah, there's, of course, this field is really crowded. So quite a lot of, also even big players are in this field. So what is the way that we make the competitive advantage is that they all rely on this, call it old principles of this heuristics. Some approaches really try to accelerate this computational intensive process by using graph, like graph or CPUs and GPUs, I mean, so to speed up the process. Other are going in the graph-based representation, but then all based on k-mers, a k-mers approach. So that's the key. And so there we make indeed the difference.
All right. Well, thank you very much. Let me, it's time to wrap up. Let me quickly add the other speakers to the stream. So if you were sleeping behind your monitor, now it's time to wake up again. I'm just kidding, they're all loud and clear there. So yeah, Jan van der Bussen, thank you very much for your talk. Your first talk of the evening was very interesting. Geert and Jan, also thanks very much for sharing. Yeah, sorry, I really lost my voice. Your knowledge about or your contributions actually to the open source world with Cobra. I'm looking forward to playing around with it. And then last but not least, Dirk and Sebastian, thanks for giving us a glimpse on the inside of what you're doing in your space with BioStrand. And I hope, I wish you the best with your startup, and I hope you'll be the next big unicorn out of Belgium, right? Thanks all for joining, and I see you next month in our 35th already Data Science Leuven meetup. Thank you very much.